Good morning, everybody. So, we are almost reaching towards the end of the enzymes bearing this particular metal center, which is very interesting, starting from their coordination chemistry and all other aspects. So, this molybdenum center, when we can have certain coordination positions which are occupied, and we find that in some of these cases you have loosely bound water molecule bound to it, and this water molecule together with some other strongly bound groups like oxo or sulfido units play some important and interesting role towards their catalytic activity. So, when we talk in terms of their coordination chemistry of molybdenum in the three possible oxidation states from +4, +5 and +6, and the relative binding properties of all these groups. Here we all know now that these two are the sulfur bearing bidentate ligand type of molybdenum class. So, if we consider these three groups and their relative binding properties towards the metal center, either in the lower oxidation state like +4 or in the higher oxidation state like +6, we just simply consider that in some cases the binding is strong and in some other case the binding is weak. And if we just simply consider that binding of any metal ion, it can be iron, it can be nickel, it can be copper or simply the molybdenum center, when any of these salts we dissolve it in water, we generate this water bound or aqueous species in solution. And in all these cases, depending upon the coordination number n and the oxidation state x, we see that in all these cases at least one of these bond is MOH2 bond. And how strong this MOH2 bond will clearly dictate us how quickly we can remove this thing by some other group or how quickly we can go for deprotonation. These are very important steps for all these molybdenum enzymes, because if we just simply go for deprotonation from here, we will be reaching somewhere where we can have MOH, and after another step of deprotonation we get that oxo species. If the center M is molybdenum, we get molybdenum oxo species. So, most possibly in all these cases, if the metal center, say the molybdenum center, is present in highest possible oxidation state, that means the +6 oxidation state, it will little bit strongly bound to that OH2 and it can change its corresponding pKa value of the water molecule. As we all know, we have a standard pKa value for the isolated water molecule, which is not bound to any metal center, but these bound water molecules can be acidic when they are bound to the metal center and which is in the little bit higher oxidation state. So, if the pKa is less, these bound water molecules will be acidic in nature, and since they are acidic in nature, it undergo deprotonation and we get molybdenum hydroxide complex if the metal center is molybdenum, and again we just can go for the deprotonation, we get the molybdenum oxo species. So, slowly moving from these two steps, we can have this particular binding point, it can have the molybdenum OH2 bond, that means the molybdenum aqua bond or molybdenum water bond, it can simply go to for the corresponding molybdenum oxo species. So, at the same time if we want to remove this water molecule, so the removal of this water molecule is important, because we can have the substrate molecules and those substrate molecules are coming into the picture in the close vicinity of the molybdenum center, and those substrate molecules will try to remove these water molecules and will go for the corresponding coordinate bond to the molybdenum center. So, if we want to have the removal of this water molecule, we should have a correspondingly weak water bound to the metal center. So, if we have a catalytically labile oxygen, so we call these as catalytically. Why it is catalytically? Because it will participate in the corresponding catalysis. So, catalytically labile oxygen we can have so we can have a corresponding labile center attached to the molybdenum. So, if this particular coordination environment is square pyramid in nature, so the geometry will immediately tells us that you can remove this loosely bound water molecule and this particular site can be useful for binding some other group, that means the substrate, if when we are talking about the corresponding oxidation reduction of the aldehyde or alcohol or any other substrate. So, this particular substrate will come and bound to this particular site to give you the corresponding catalytic activity. And another case is also important to know here, that in all these cases, that means if we have a metal center like say iron, when we dissolve it in water, say ferric chloride. If we have ferric chloride and the ferric chloride is dissolved in water, we get the corresponding hexa-aquo complex of the ferric ion. And this hexa-aquo complex of the ferric ion can, we all know that the corresponding determination of concentration of iron can very easily be done by using thiocyanate anion, because this particular bond which is forming there, that means the thiocyanate bond, by removal of one of the water molecule. So, you remove one of the water molecule and thiocyanate is going there and attaching to the iron site. So, this particular thing is highly colored. So, it is blood red in color and we can determine the corresponding concentration of the unknown iron present in the system or unknown concentration present in the system. So, the formation of this particular type of bond, which is nothing but the removal of the water molecule and the introduction of some other group to that position, such that the corresponding iron nitrogen bond is stronger compared to our iron oxygen bond. Such thing also happening in case of these molybdenum based complexes or molybdenum based enzymes. So, if we just simply react with this, and if this catalytically labile site is reacting with any of these anions, inorganic anions, say thiocyanate anion or cyanide anion or azide anion. So, all these things are very useful in studying all the different types of metalloenzymes, because if we have a loosely bound site or a water bound site, it immediately go and replace those water molecules and occupy those positions because the molybdenum oxygen bond is little bit weaker. That is why we are talking in terms of the corresponding, not in terms of the corresponding weakness or strength, but also in terms of its corresponding reactivity in the kinetic term, that means which is not inert, but is labile. So, the lability of the complex, corresponding complex is important, and we get the corresponding binding of the molybdenum site by nitrogen of thiocyanate or nitrogen of cyanide or nitrogen of azide. So, due to that substitution, so these can go and bind to the molybdenum center. So, due to this substitution, what we find that this catalytically labile oxygen is removed, that means the water molecule is removed and this position is occupied by some small inorganic anion. So, these small inorganic anions, if after binding to the molybdenum center, if we see that the same molybdenum enzyme is not catalytically active for the reaction, we can say that these are strongly bound to the molybdenum site and the substrate is not able to reach to the molybdenum site and is therefore getting inactivated. So, we can say also that inhibition of that corresponding enzymatic activity is done. So, this is one way of replacing this water molecule, and that can also establish that how important is this catalytically labile site. That means, whether you should have a bound water molecule to the molybdenum site for catalytic activity or not. And in the second case, that means how these two positions, because these are the three positions of debate, that whether the oxo site or the thio site are equally important to go for corresponding catalytic activity. So, if we can not see the removal of this water molecule, but we can go for some of these, that means these groups, particularly this Cn minus, this can also very well attack on the corresponding oxygen or corresponding sulfur on the molybdenum site. What happens there? Then they are producing CNO if Cn is attacking on this oxo bound to the molybdenum center. So, it is forming cyanate anion, or this Cn minus is attacking to the sulfur, it is forming NCS, which is thiocyanate. So, these two informations, that means whether you can have a simply a cyanide bound molybdenum center or thiocyanate bound molybdenum center from the introduction of Cn minus to the reaction site, we can immediately say that this oxygen or this sulfur has been converted to the cyanate ion or the thiocyanate ion, and during that sort of coordination the molybdenum site reactivity can also be lost and its corresponding enzymatic activity can also be lost. So, we can have two such inhibition. One is the direct inhibition by removal of the catalytic water molecule, or the catalytic site is not there and some other positions are occupied by some other groups, or the conversion of the cyanide group to cyanate and thiocyanate. So, that also tells us that how these two sites are also important for the catalytic activity. So, the inorganic anion like the cyanide, azide or thiocyanate. So, this Cn minus can be a very good inhibitor for these molybdenum site. So, is inhibitor. So, this inhibition we are getting from small inorganic anion. Inorganic anion. but also we will see that since the site is we are talking about, and we are talking about some removal of water molecule by some group or the conversion of some of these groups to useful oxygen or sulfur derived inorganic anions, because we can have oxygen derived and sulfur derived cyanate and thiocyanate anion, and these two oxygen and sulfur source are from the molybdenum site. So, you can also use here the corresponding oxo anion, and this particular oxo anion, so any oxo anion, so can be our phosphate, then arsenate, it can be nitrate, it can be perchlorate. So, these are the different oxo anions. So, these oxo anions can also go to the metal center and bind there. So, if we have the molybdenum site, and already we have seen that water is bound to this site, but we will find that compared to water, some of these oxo anions are weakly coordinating, and these weakly coordinating groups will not replace the water molecules, because they will also remain as the corresponding typical anion outside the coordination sphere, and we get the corresponding conductivity value related to the non-coordination of the nitrate anion and non-coordination of the perchlorate anion to the molybdenum center. So, we are having this thing, that means we have this corresponding sulfur and the corresponding oxygen groups, and this particular one, if we just think of for the corresponding arsenic based anion, which is arsenic plus 3, so which is arsenite. So, this arsenite, again another form is SO3 3 minus. So, these are arsenites, which are different from the corresponding oxidation state of plus 5, which are arsenates. So, between these two species we see that the corresponding variation in the, because the arsenic oxidation state in both these two cases are plus 3, it is only the change in the oxygen content of the corresponding oxo anions, like that of is nitrate and another well known species we know, that is the nitrite. So, the nitrate and nitrite both are oxo anions, but having different nature of the nitrogen atom as the center of that oxo anions. So, these things, if we just now extend our idea what we are discussing for last several minutes, that when we can have this binding for this Cn minus, which is inhibitor, it can go and directly bind to the molybdenum center, or it can interact with the oxo anion or the thio anion bound to the molybdenum site. So, the binding form of the corresponding oxo anion to the molybdenum site is important, and if we find that this oxygen is involved to react with ASO2 minus and converting the entire species as ASO3 minus, because this oxygen can now have the competition of sharing between the molybdenum site and the arsenic site. So, what we are doing? We are doing something that we have the labile position here, we have the oxo site and we have the thiol site, and these groups, particularly these oxo anions of arsenic or the molybdenum, because the molybdenum have equal affinity for binding to sulfur as well as oxygen, because molybdenum, we all know that molybdenum can form tetraoxo species or molybdenum can form tetrathio species. So, these two immediately tell us that whether this particular anion or this anion, say this one having less amount of oxygen, because we think that we are providing either oxygen or sulfur from the molybdenum side, and it is not going to bind alone from this labile site. So, the change in this thing, that means the change in the nature of the corresponding group, that means whereas we are using ASO2 minus and converting back to ASO3 minus, and with the donation of this oxygen, this oxo anion from the molybdenum side, what we are doing? We are engaging this particular site as well as this labile site, because the water will be removed ultimately, and the entire arsenic site, the arsenite anion will bind to that molybdenum site. So, that serves the purpose of replacing this particular catalytically labile site as well as engaging the oxygen for the corresponding attachment to the arsenate site. So, that we have seen from our last day's thing, that what we have started our discussion there, that arsenite is also available there, and this arsenite anion can inhibit the xanthine oxidase. So, we have this arsenic in the +3 position oxidation state, and when sulfur is involved, so between these two, that means molybdenum and arsenic, we have the corresponding competition for the sulfur binding, because this entire group what is there, that means arsenic, 1 sulfur and 2 oxygen can be a very useful mixed oxothioanion of arsenic, which can bind in this fashion and can remove from the system. Also the same arsenic, that means ASO2 minus, can directly bound to the corresponding sulfur site and providing this particular site as the protonated site. So, whether the essential site is the oxo site or the sulfur site, so the catalytically essential sulfur is also essential for the high affinity of the reduced xanthine oxidoreductase for arsenite. So, this sulfur is essential for our catalytic activity, and this sulfur is also essential for arsenite, that means this sulfur is helping this binding of this arsenite group to the molybdenum side. So, this is well known, that means the arsenite is known for long time, that it can come into the picture and just go for the corresponding xanthine oxidase activity reduction, and since it is tightly bound compared to the loosely bound water molecule or loosely bound any other substrate, it is particularly tightly bound to the reduced form of the enzyme, which is very important, the reduced form. So, the enzyme what we are talking about in all these cases, the molybdenum in 6 plus, molybdenum in 5 plus, and molybdenum in the oxidation state of 4 plus. So, all these cases, as I told previously, that this particular system, that means whether the binding of any other group, whether it is forming the oxoanion, whether it is forming the thioanion, or the binding of the substrate molecule or binding of the water molecule to the system, is depends on the corresponding oxidation state. So, this arsenite basically when it goes is particularly binding tightly to the reduced form of the enzyme, where the molybdenum site has been reduced to +4, and at the same time it provides the corresponding structural basis for understanding the inhibition of the enzyme. We are able to inhibit the corresponding activity of the molybdenum enzyme for this by attaching arsenite to this, and which simultaneously blocks the equatorial MOH ligand that initiates the nucleophilic attack on the substrate at the outset of catalysis. So, when we start the catalysis based on molybdenum, we can have the molybdenum OH bond also, and we can have the molybdenum sulfur double bond. So, the molybdenum sulfur moiety that serves as a hydride acceptor during the course of the reaction. So, if this particular MO double bond S is getting converted to MO single bond SH group. That means, this sulfur functioning as a very good hydride acceptor for this particular reaction, because the initial activation of any substrate species or any other species involves the attachment of this hydrogen atom in the form of a proton or hydride to any of these groups, but the molybdenum site does not have the corresponding affinity for binding proton or binding hydride anion. It is the group which is already attached to the molybdenum site, that means the sulfur or the oxygen site, which can take care of the hydrogen atom or ion in the cationic form like the proton or in the hydride form as the anion. So, ultimately what we get this particular arsenic site. So, arsenic is tri-coordinated. So, arsenic site is little bit is planar arrangement. So, this plane, this arsenic plane is coming close to the another plane where the molybdenum site is there, which is in a square base of 3 sulfur and 1 oxygen, little bit above the square base. So, these two planes basically, this plane S3O plane around molybdenum and SO2 plane around arsenic, they are almost coplanar. So, they have this thing, that means in case of arsenic, when it can expand for a 4 coordinated geometry by attaching some other group, in this particular form it can be trigonal by pyramidal geometry, and in the 3 coordinate form is the trigonal planar geometry in the reduced complex. So, the reduced complex means the molybdenum site, we are not talking in terms of the corresponding inhibitor which is coming as molybdenum on the surface of the molybdenum as arsenic. So, arsenic is already in the reduced form, that is why we are talking in terms of the arsenite inhibition, not the arsenate inhibition, but the enzyme is also in the reduced form. That means, this enzyme is can be in the +4, and for the settling for the enzymatic activity it can go up to +5 oxidation state from the +4 oxidation state. Now, we just see the corresponding handling of these enzymes by aldehydes. So, how aldehydes can be there and how aldehydes can be useful for the corresponding oxidation to the center. So, aldehydes can be very easily take up one of the oxygen atoms, what we are talking about the corresponding hydroxylation in case of xanthine oxidase for xanthine hydroxylation. So, aldehydes can very easily be oxidized to form the corresponding carboxylic acid group. And now, this oxygen based on the molybdenum site can very easily transfer that oxygen to the aldehyde site. So, one group of these molecules which are known as AOR. So, aldehyde oxidoreductases. So, these aldehyde oxidoreductases bearing the same molybdenum site can go for the redox reactions, and those redox reactions still involving these 3 oxidation states of molybdenum, which are very easily accessible to us. So, these AOR families like xanthine oxidase family, which are XO family. So, these are another group of molecules which are aldehyde oxidoreductases, we call it as AOR. And when we consider these depending upon their different source, that means the biological source what we can have, suppose we can have the disulfo-vibrio gigas. So, where the disulfo function based on the molybdenum is available. So, we just level it, so which is the DGAOR. So, disulfo-vibrio gigas would be DGAOR, that means it is still an aldehyde oxidoreductase, responsible for the oxidation of the aldehyde function. So, immediately we identify that this also contains a molybdenum site. So, identification of this site as molybdenum is important, which catalyzes the oxidation of aldehyde. Just now what we have seen, that it can be very easily converted to the corresponding carboxylic acids. So, some of these groups basically, if we see that what we are just talking right now, that you can have this aldehyde oxidoreductase family, we are now talking not in terms of one sulfur, one oxygen, but is the molybdenum dioxoform, which is well known to us also from the days of the corresponding complexes, the coordination complexes of molybdenum. What we have seen that the molybdenum acetyl acetone complex. So, these are also well known compounds in the cis variety, that means these two molybdenum oxygen groups are in cis positions. So, they are roughly 90° apart. So, one more site is available for this and two other from the pterine part, that means the sulfur bearing molybdopterine part is coming into the picture. So, this is, as I told you just now, that this disulfo-vibrio gigas, which is the biological naming of the origin of these molybdenum enzymes, and the family belongs to AOR, that means aldehyde oxidoreductase. So, just now we have seen also that arsenite inhibition, how it does. So, in the +6 oxidation state, though it is very easily binding to the molybdenum in +4 oxidation state, but it is still bound to the molybdenum site in the +6 oxidation state. So, these two oxo groups available, and the third one is the corresponding arsenite group attached to the molybdenum site. We can have also, so this is typical inhibition with respect to the arsenite. Then you have the disulfo form, that means no sulfur group is attached there. So, it is known as inactive disulfo form and the active form. So, to begin with the catalytic cycle, it starts simply with 1 oxo 1 sulfur form. So, this 1 oxo 1 sulfur form, when it goes to a dioxo form, we consider it as a inactive disulfo form. That means, this has lost the corresponding activity towards aldehyde oxidation. So, which means immediately to us that the presence of this sulfur is therefore very important. Without this sulfur, we cannot see the corresponding catalytic activity. So, when you remove this sulfur, your activity is lost. So, in relation to the corresponding molybdenum sulfur double bond or molybdenum thione form, so this molybdenum thione form should be there in the active form, but if we can convert it to a disulfo form, it would be inactive. So, the presence of this sulfur group is important for catalytic activity, as well as the presence of this Lewis site, that means OHX, binding of OHX. So, here what we are seeing, that we are binding something which we are labeling as OHX. Why OHX? OHX means during the catalytic cycle it can be OH2, that means the water molecule attached to the site, or it can be OH. That means during this particular point, that means depending upon the molybdenum oxidation state, whether it is in the +4 oxidation state or some other oxidation state, the bound water molecule can immediately go for the deprotonation, and you can have a hydroxido function attached terminally to the molybdenum site. But the catalytic activity for these two groups, that means the catalytic activity for water bound molybdenum site and hydroxide bound molybdenum site are different. So, initially identifying that immediate positions, that means we can have for a active site a bidentate sulfur chelation, SS chelation from the bidentate group, oxo function, the thione function and the OHX function. So, you can immediately write the coordination environment. As a typical coordination chemist, we are always interested to know what are the immediate groups which are bound to the metal site, which are bound to the molybdenum site. So, the coordination around the molybdenum atom for the xanthine oxidase family of enzymes is therefore, we have this OHX is considered as OH after deprotonation from here, and this is something where the enzyme is providing a typical base. So, nearby base sometimes we label it as B minus or BH plus. So, B minus, which is the base originating from the enzyme environment, that is very important, because this particular base, like the way we do the corresponding chemistry in the laboratory, we externally add some base for deprotonation of the ligand or deprotonation of the water molecule which is attached to the metal site. But when we are talking in terms of the enzyme, so this particular B minus is of enzyme origin. So, it is coming from enzyme. So, this particular one is therefore very important, because it can take off this proton from water molecule or another proton from the hydroxide ion to control the reactivity. So, what is happening there, that we are talking in terms of the corresponding oxidation of the aldehyde function. So, aldehyde will be there. So, that aldehyde is written in terms of RCH without showing the oxygen already present in the aldehyde function, because if we consider that RCH as the aldehyde, it would be very much similar to that of our substrate what we earlier seen in case of xanthine family. That means, what we are doing there, we are doing something which can again be considered as a hydroxylation reaction. That means, already we are having one carbon oxygen double bond, but still we are able to go for another hydroxylation level. That means, another oxygen can be attached to this carbon to make this carbon as the carboxylate group. So, when this OH is attached to the molybdenum site, this glutamate anion, which is the basic site provided by the enzyme. So, the glutamate anion, that means the residue is based on the glutamic acid, and that glutamic acid in the deprotonated form, that means O is present as minus O minus. So, glutamate anion is there, and that glutamate anion will have some affinity for the proton which is nearby attaching to the molybdenum side. So, reversibly this can take off this hydrogen ion as proton to the oxygen site as O minus, that means the basic site of the glutamate anion coming from the protein chain. And when it is coming to this oxygen, this O is getting some accumulation of negative charge, that means it is becoming O minus, but at the same time it is not forming the corresponding double bond to the molybdenum center, but this corresponding basicity or the nucleophilicity will allow this oxygen to attack the carbon of the carbonyl function of the aldehyde. So, this is facilitated by the base. That is why we consider this as, which is a very important statement, like any organic chemist statement, that base assisted nucleophilic attack. So, base is there which is assisting the liberation of proton from the OH function. So, OH having lone pair of electrons, in fact it is there also in water molecule also. Water molecule also bears some amount of lone pair, that means 2 lone pair of electrons are there on the water molecule. So, the availability of those 2 lone pairs for any kind of nucleophilic attack is there, but which can be assisted, that means which can be enhanced. The nucleophilic character can be increased if we just go for the corresponding deprotonation of 1 proton from water molecule to hydroxide anion, or the second proton to go for its corresponding O2 minus. So, this O2 minus basically will have higher nucleophilic character to attack the carbon center on the aldehyde function. So, you have COH and R group of the aldehyde group. So, this will basically go for nucleophilic attack on the carbon center. So, that attachment of this proton to the glutamate acid will assist the nucleophilicity or increase the nucleophilicity of this oxygen to be attacked on the carbon. Since it is a nucleophilic attack for that, so electrophilicity of this particular carbon, that means the carbonyl carbon, should have to be increased if we can take out this particular hydrogen attached to this particular carbon center. So, if this we can take out as the hydride anion, so this can go to the sulfur nearby already attached to the molybdenum. So, this sulfur can take off the hydride anion. So, it is basically losing this corresponding hydride to the sulfur. So, this hydrogen is moved from this carbon to sulfur, making this sulfur as SH group. So, when it is moving the SH function, this oxygen already attached to this molybdenum site, but can now nicely attack this particular carbon of the carbonyl function of the aldehyde group. So, we can have this particular oxygen in between molybdenum and the carbon site, and in that way we have transferred this oxygen from the molybdenum side to the carbon side. That means, we have formed a new carbon oxygen bond mediated by molybdenum oxygen bond. So, we can have the bridge between molybdenum and carbon side by oxygen which was already present as OH function attached to the molybdenum. So, we have this, that means RCO. So, basically RCH was the aldehyde. So, this has been converted to a carboxylate function. So, this carboxylic group and the attachment of the SH, we need the transfer of 2 electrons also, and those 2 electrons are basically donated to the molybdenum site, and molybdenum site is reduced from +6 to +4. So, this particular site is now very important, that molybdenum 4 is attached to the carboxylate function, and this particular one is a catalytically transient state, that molybdenum 4 is there and SH function is attached to molybdenum 4, and this molybdenum 4 will have some immediate tendency to be oxidized to molybdenum 5, because the corresponding E0 value is less for the corresponding electron transfer couple, halfway potential between this molybdenum 4 and molybdenum 5 is less. So, it can go for first the electron transfer followed by a proton transfer from this sulfur. So, it has been accepted this hydrogen as hydride anion, but now it is losing this as a proton H plus, such that you can have as S minus, and it will revert back to original sulfur double bond molybdenum, and your molybdenum site is being stabilized here in +5 oxidation state. So, this is the carboxy end. So, carboxylate bound molybdenum 5 is the typical intermediate form, where we have converted the aldehyde function to the carboxylate function, and after that conversion it is still attached to the molybdenum site, and which is very much similar to the binding of several other species, where we know that the metal salts we can have as the corresponding carboxylates. The typical examples are as the metal acetates, like corresponding copper acetates, corresponding chromium acetates, and all these. So, if we can have the corresponding molybdenum is there, and we consider it as the corresponding OAC type of thing. So, this is a useful arrangement for binding of acetate or any other carboxylate function. So, carboxy groups can go and bind to the molybdenum site. So, this can function as a weakly bound ligand center to the molybdenum site. So, when it is attaching to this particular site, our corresponding enzyme function based on the corresponding glutamate base is still there in the acid form. So, it is in the glutamic acid form. So, MOOH function on the carbonyl substrate attack, that means MOOH function on the carbonyl substrate are ultimately producing that carboxylate group attaching to the molybdenum site, and we have the glutamate function residing there close by as the corresponding acidic form. Now, this acidic form of the glutamic acid, which is not a part of the molybdenum site in the catalytic site, but this is nearby. Now, it is acidic in nature. When it is converted to the corresponding carboxylate function, it can immediately supply this particular proton to this bound carboxylate anion. So, like acetate anion, which can be bound to any metal center, this carboxylate site cannot be stabilized as a bound site to the molybdenum when we can have a nearby free acidic site. So, the free glutamic acidic site from the protein side chain is more acidic and can supply this proton to this carboxylate function to make it typical acid, and once it is protonated, it will not be attached to the molybdenum site, and it will simply remove from the molybdenum site, and one vacancy will be generated over here, and that generation of that particular vacancy will next be occupied by simple water molecule to that particular site. So, our catalytic site can be regenerated by transferring this molybdenum 5 to back to molybdenum 6 through this removal of this proton from here as OH. So, what we see here that the most accepted reaction mechanism, what we have seen just now, that the corresponding reaction mechanism implies that we should have a base assisted nucleophilic attack. So, definitely we should have a attack which is nucleophilic in nature, but which should be assisted by the corresponding glutamate base nearby, and the carbon atom of the aldehyde group is hydroxylated by the OHX ligand, and concomitant hydride transfer to the sulfido ligand. This all I just now I told you, where the nearby glutamic acid residue acts as base for the proton of the OHX ligand, enhancing its nucleophilic character. So, how nearby glutamic acid residue can enhance the corresponding nucleophilic character of the bound ligand to the molybdenum site. So, what we see, which is very interesting to note here, that this OHX ligand, is nothing but our reagent for the corresponding reaction, that means the oxidation reaction of the carboxy function of the aldehyde to the carboxy function of the acid. So, if we have the origin is disulfovibrio gas and AOR is coming out from that, so it also belongs to the bigger family of xanthine oxidase bearing mononuclear molybdenum center, and now the catalysis is little bit different. It is involved in the oxidation of aldehyde to carboxylic acid. So, together OH and OH2 ligands, we can call it as, wherever we find this on the molybdenum, we can consider it as OHX ligand. OHX ligand means that it can be OH or it can be OH2, because sometimes it is very difficult to identify whether the center is OH or OH2, because if we can go for the corresponding protein crystallography also and through X-ray diffraction, it is very difficult to identify the number of hydrogen atoms attached to the oxygen site. So, it is very difficult to identify whether the group is OH or OH2. So, some other indirect evidences we must sort for to clearly identify the nature of these groups, and already we have discussed, we have established that the binding of this OH and OH2 ligand to the molybdenum site is definitely the corresponding labile site of the protein, and when substrate or inhibitors can come, it can bind through that particular site only to the molybdenum. So, you can ask the question that which particular site is therefore responsible for binding of inhibitor, for binding of the substrate, and what are the other groups involved for the corresponding catalytic activity, because it is a very much complicated one for the proton abstraction as well as the hydride transfer from the corresponding substrate molecule. So, all these things together can give us some very good idea about what is happening there for the corresponding simple case, that means the corresponding simple oxidation of aldehyde, because aldehyde oxidation is not a very difficult task. In air also synthetically prepared or laboratory available aldehyde molecules can go for immediate oxidation through the air. But when we are talking in terms of the corresponding concentration in the biological system, in the living organisms, the corresponding reaction is little bit complicated, where we take the help of molybdenum. So, in all these cases, or if we take that particular disulfovibrio gas AOR, and if we want to have some informations whether your molybdenum site is stabilized or the molybdenum site is there in the catalytically end point, whether that is a molybdenum 4 or a molybdenum 6 or really a molybdenum 5. So, we can use something, that means the addition of ethylene glycol and glycerol to the system where we can have the dithionite group. So, dithionite is a very useful reagent for reducing this particular site, that means the molybdenum site, because not all chemically available or biochemically stable reducing agents can reduce the corresponding molybdenum site from molybdenum plus 6 to molybdenum 5, because in all these cases, particularly in the biological environment, we can have the corresponding E0 values for the reduction of molybdenum plus 6 to molybdenum plus 5. So, we have the corresponding E0 value for the reduction. So, it can be some millivolt only. So, depending upon the corresponding available potential for molybdenum, we can have the dithionite anion. So, dithionite, which is little bit a strong oxidizing reducing agent compared to other reducing agents. So, this dithionite also can have the corresponding reduction potential E0 value. So, if these two potentials, the potentials for molybdenum center reduction and potential for the dithionite based reduction is matching, and if this is higher, if this is E1 and this is E2. So, if E2 0 is higher than E1 0 on the reduction side, you are able to reduce the molybdenum from +6 to +5. So, the molybdenum center what we are getting, we are just simply trying to establish the site as available oxidation state of molybdenum during the catalytic turnover, whether that particular molybdenum site we are getting is EPR active, and between these three oxidation states of molybdenum, only molybdenum 5 having one particular unpaired electron which is EPR active, and it gives a corresponding rhombic nature of the signal. Rhombic nature is nothing but we can have three different G values basically. One is known as G1, another is known as G2, and third is known as G3. So, basically your all these three different sites, that means X, Y and Z are different around molybdenum. So, we get the corresponding G tensor in the EPR spectrum different. So, instead of having one particular G value, which we call it as the corresponding isotropic signal, we get a splitting of that particular isotropic signal into 3, and the nature of this signal can be known by knowing the corresponding values of G, that means what is the value of G1, G2 and G3, and their corresponding line width also, their typical positions and the shape, which is very important. So, for these molybdenum 5 site, which has a very good database for knowing the corresponding shape of the typical molybdenum 5 sites. So, the biological sites, if we get the similar type of spectral signature, we can immediately say that you see the molybdenum 5 is involved in the catalytic cycle, because it has a similar EPR signal what we know from other synthetically prepared molybdenum site or other biologically known molybdenum site like that of our xanthine oxidase. We can say that this signal having some values of G1, G2 and G3 and the corresponding shape which we are talking in terms of rhombic, which is not isotropic, which is not axial, but is rhombic. That immediately confirms something, that it has nearly a square pyramidal coordination geometry of the active site and is distorted upon alcohol inhibition. That means, when we use glycol or glycerol, we just looking for the binding of the molybdenum site by replacing the weakly bound water molecule by the OH function of glycerol or OH function of the glycol. So, that alcohol inhibition is still there, and that alcohol inhibition is responsible for the signature what we are getting. So, the EPR spectral studies is little bit complicated. It has taken from Journal of American Chemical Society of different issue of 2009. So, which gives us some example that what are the typical values in this scale of 1.90 to 2.05. And this is the first signal, this is the second signal and this is the third signal, and how they are changing, and the dotted lines are also we can go for the simulated one. That means, theoretically we can predict these values for changing the different parameters, and sometime low temperature is also required, like liquid nitrogen temperature or liquid helium temperature. and this is the corresponding signal for the reduced form, and this is the reoxidized form. So, these two things are basically sometimes changing, and apart from the positions for molybdenum. So, this is G1, this is G2, and this third one is G3, and not like this what just now we have seen, they are little bit overlapped in nature. That means, the values, the difference in G1, G2, G3 are less, and there are several other signatures also available if we can have other paramagnetic sites. So, in all these cases some iron sulfur bond systems are there which are responsible for giving electron transfer to the molybdenum site. So, at some other lower temperature where we can go for 4 Kelvin in liquid helium temperature. So, this particular one can also show some other values, and those particular positions can be identified nicely as the corresponding signature for the molybdenum sulfur clusters which are paramagnetic in nature. So, the entire EPR signal which is getting complicated or which is also getting disturbed little bit if we have some other nearby paramagnetic site like that of iron sulfur site. So, simulation of these values basically, that means involving iron site or involving the molybdenum sulfur site, can tell us some idea about the corresponding G values, that the what are the corresponding G values which can immediately tell us that whether we can have 3 signals or 2 signals. So, next day we will just continue from here, that how these EPR signals apart from these structural identifications are useful for our identification. Thank you.